Welcome to week 6, guys. We are going to talk about two different topics this week. We're going to kind of split the week in half a bit. We're going to talk about hurricanes in Chapter 11 and then air pollution in Chapter 14. So let's start with a top-level view and a top-level discussion of hurricanes. Chapter 11 is all about hurricanes. Whether you call it a hurricane, a cyclone, or a typhoon, those are all the same things. It's just changing the name based on your regional location on Earth. It's different places of the world call them different things just because that's what the culture has ended up naming them. So if you go into East Asia, depending on how far north or south or how close you are to the mainland of Asia, it's either going to be a cyclone or a typhoon. Most places like China, Japan, and Indonesia, it's a typhoon. The farther south you go towards Australia, it becomes a cyclone. Again, it's cultural differences. But they are all the same thing. It's a hurricane, but just with a different name. And then, of course, in the southern hemisphere, they're spinning a different direction. So there's three different kind of categories of these tropical disturbances that we talk about, and those are based on speed. So it starts with a tropical depression, then it goes up to a tropical storm, then it goes up to a hurricane. The classifications of those are based off of how fast the surface wind speeds are actually blowing, and it's certainly not arbitrary. The damage scale of those is affected by the wind speed as well, but the classifications are strictly speaking based off of the wind speeds. Now, the structure of a hurricane is pretty simple. It starts with the eye, and then around that eye, so the eye is absolutely calm. It might have some clouds, but it's actually usually pretty sunny and a very well-organized hurricane. So calm eye, right around the eye is where we see the strongest winds and where the maximum damage will occur. That is the eye wall. It has a lot of very heavy rain, thunderstorms typically in a perfect circular pattern around the eye, and that's when you see the highest winds and highest storm surge. And so that's why the highest damage is located there as well. Out from that, we have these spiral arms. If you've ever seen a picture of a galaxy, it kind of looks like those spiral arm galaxies, or just think of like a pinwheel, like a kid's toy. It looks like that. Those spiral arms spiral inward towards the hurricane eye, and basically they're bands of thunderstorms that spiral inward. So what causes tropical depression, tropical storm, to mature or to develop into a hurricane? Basically what fosters that development? The key in all of that tropical development, those tropical storms, is warm ocean water. The latent heat content, as well as just the sensible heat of the water, is enough to really fuel those storms. That being the main ingredient, there are quite a few other things that will foster the growth of those storms. For instance, you need high relative humidity through the entire depth of the atmosphere. If you don't have that, you actually can get evaporation, and that would cool off the column, which would actually hinder your hurricane development. So high relative humidity throughout the column, throughout the atmosphere, at least through the troposphere, and then low wind shear. As powerful as these systems are, if there's shear, remember what shear is. Shear is wind changing speed or direction with height in the troposphere. If the shear is high, you can actually shear apart the hurricane. Hurricanes don't work the same way severe thunderstorms do that produce tornadoes. Shear in the atmosphere is not good for them at all. So it will blow them apart. So we need low shear. We need easterly waves. Easterly waves are just these little ripples in the atmosphere that cause either surface convergence or upper level divergence. So surface convergence causes the air to come together and forces it to rise. Upper air divergence causes the air to separate, but there's no vacuum there, so air will come up from below, and both surface convergence and upper level divergence cause upward motion, and you need upward motion for cloud development, and that fosters then hurricane development. If you have a large complex of storms already ongoing, that will also help hurricanes to develop into depressions, then the storms, then the hurricanes. Of course, having a thunderstorm isn't enough. You need the last, maybe one of the other most important ingredients, and that's the Coriolis force. You have to get that complex of storms away from the equator, because the equator has zero Coriolis force. So if you get a storm, you almost have storms year-round around the ITCZ. It's very close to the equator. But you don't have hurricanes all year round on the ITCZ because those thunderstorms aren't affected by the Coriolis force because it's so weak there at the equator. So the farther those storm systems, those blobs of storms, if you will, get away from the equator, the more the Coriolis force affects them, and the more likely they are to start to swirl into your hurricane. Now, the unfavorable conditions are going to be just the opposite. If you get cold water, for instance, you're going to take apart you're going to remove the fuel for your hurricane pretty quickly. If you go over land, you're going to also remove the fuel for your hurricane because you've basically removed the warm water. The land may be warm, but that's irrelevant because you've removed that warm water, that really moist air. You also have drag effects over the land that you don't have over the water. If you pass a hurricane over mountains like Hispaniola or mountains of Cuba, you will tear your thunderstorm apart because of the drag effects on the wind. If you add shear into the entire environment, you'll tear it apart. Basically, any opposite of the favorable conditions are going to deter your hurricane development. One of the which, like I said, is if your hurricane isn't far enough away from the equator, you're probably not going to be able to get it to spin up, and it's probably not going to develop into a hurricane. So, interesting how that works. So, the other thing about that, the farther away you get from the equator, you obviously get more Coriolis force because it's maximized at the pole. But the farther away you get from the equator, the farther away you get from warm water. So there's kind of this happy zone of where hurricanes are most likely to develop. As you're reading in chapter 12 about hurricanes, you might start thinking, well, why does a hurricane form and not a mid-latitude cyclone? They're both low-pressure systems in the northern hemisphere. They're both rotating counterclockwise. So why are they so different? Why does a hurricane form and not a mid-latitude cyclone? Or why don't we have hurricanes over the United States? Why do we not have eyes in the center of a low-pressure system in the United States like we do over the tropics? Why are there differences? Fundamentally, the differences are due to something called warm core systems and cold core systems. Warm core systems are hurricanes. Cold core systems are mid-latitude cyclones. Really what that means is a mid-latitude cyclone has a cold core in the upper atmosphere, where a hurricane is warm throughout the entire atmosphere, relatively speaking. What that also means is a mid-latitude cyclone is strongest up above the surface towards the tropopause, where a hurricane is strongest near the surface, that's where the winds are going to be strongest. So, and there's no jet stream associated with a hurricane, otherwise its shear would tear it apart. So think about it that way, and since we have the jet stream in a mid-latitude cyclone case, the winds are strongest up aloft, where since we don't have a hurricane, since we don't have a jet stream in the terms of a hurricane, the winds are strongest near the surface. Other considerations. Hurricanes, everywhere around them is warm. So if it's blowing from the north or from the south, it doesn't matter. It's still blowing warm air. So there's no fronts. It's not moving. The air mass is the same everywhere. It's an MT air mass. It's a maritime tropical air mass everywhere. So you're not changing the air mass by the differing wind directions. So there's no fronts. Mid-latitude cyclone, if you have winds from the north, you're bringing in a continental polar. So it's colder, so you have a cold front. If your winds are from the south, you're bringing in an MT air mass, so you bring in a warm front. So that's why another difference is the mid-latitude cyclones have fronts because they're bringing in different types of air mass depending upon the wind direction. Hurricanes don't have that because everywhere around them, basically the air has the same characteristics. There are quite a few other differences between the two, and I'm going to leave the discussion off right there and let you guys explore that. That will be something that will come up in some of your work for this week, so I will let you explore that a little bit more, but that should give you kind of a head start on that. Hurricanes in the scheme of the world heat balance are actually extremely important. They transport lots of heat from the equator towards the pole regions. But in so doing, they can cause a lot of damage. They only really matter to humankind once they start affecting the land. And when they do, they can actually bring in quite a bit of damage. So what types of damage can they bring in? Well, certainly wind. Wind is usually what people think of pretty quickly. But the two most important, or the two most high impact events are dealing with water. One is flooding, because so much rain falls over such a wide area, you can have widespread flooding impacts. But the most high impact, though not quite as widespread, is the storm surge. The storm surge occurs when the wind is blowing from a certain direction for such a long period of time that it actually stacks the water up. Think back to a bathtub. Take a blow dryer, or step it up a little bit. Let's take a leaf blower to that bathtub, and we start blowing the water in that bathtub to one side, and it starts stacking up on that one side. That is exactly what a hurricane does. It has winds that are blowing the water a certain direction for a long period of time. That stacks that water up, and then when it hits the land, it's kind of like a mini tsunami in a way. And it hits the land with a great deal of force. It can knock over buildings or wreck beaches. Certainly we saw this pretty badly in the Gulf of Mexico when Hurricane Katrina hit. We've seen it in other hurricanes. Basically, it's that ocean actually rushing much farther than high tide can ever get, and then pulling that back out to sea. It's a very deadly event if you're ever caught in it. And Hurricane Katrina, some of the storm surges got up to 30 feet above sea level. So if you're anywhere close to the ocean at that time, basically it's devastation. So wind, flooding, storm surge. Not as widespread is the threat for tornadoes. This usually happens on what's called the right front quadrant. So follow the motion of the storm, look to the front and the right, and that's where you can have tornadoes. Tornadoes can occur in this area because of high shear. High shear. Joel, I thought you just said that hurricanes don't have or can't develop in high shear. That's right. Hurricanes can't develop in high shear, but what's crazy is, especially when they hit land, the drag of the wind on the drag caused by the land on the wind causes the wind at the surface to turn inward towards the center of the storm, and that causes extreme directional shear in the right front quadrant of the storm. And tornadoes need high wind shear in order to develop. So any thunderstorms that develop in the right front quadrant are able to tap into some really extreme shear, and you can get quite a bit of tornadoes to develop in certain hurricanes in the right front quadrant. So those are kind of the four main high impact damage sources for hurricanes. So why do hurricanes move? That's the next thing I want to address. There's not a whole lot of wind in the tropics. There's a little bit of an easterly wind, and that generally drifts them from the east towards the west. But what causes them to turn in certain directions? Well, it's the expanse and the size of the Bermuda High in the Atlantic, or the Pacific High in the Pacific. Most of the impact of hurricanes in the United States is on the Atlantic. So I want to focus on the east coast, Gulf of Mexico, just for the couple minutes here. Let's pretend the soccer ball is the Bermuda High, and the expanse of the Bermuda High is the roundness of the ball. Okay? So there's your Bermuda High. My hockey puck is going to be the hurricane. If the Bermuda High, well, let's pretend my face is the United States. If the Bermuda High were, say, to the southeast of the United States, and a hurricane were to come around, it might hit the southern tip of the United States. Let's say instead the Bermuda High moved over here, and the hurricane came around the Bermuda High. It would now hit the right portion of my face. The hurricane cannot go through the center of the high pressure, otherwise the Bermuda High would actually destroy it. A lot of subsidence to the Bermuda High. The subsidence does not support thunderstorm development, which would absolutely kill tropical depression storms and hurricanes. So what hurricanes do is they find the sweet spot around the periphery of the Bermuda High. That means that where the Bermuda High is centered will dictate the eventual curving path of the hurricane. If the Bermuda High, say, is far enough out to sea, a hurricane might come up towards the United States and then curl away. That often happens for most hurricanes. The United States is spared because the Bermuda High is far enough away, and the hurricane tends to approach the United States and then curve away because it's following basically the curve or the expanse of the Bermuda High. Where the Bermuda High kind of extends to and then fades away, that's where the roadmap, so to speak, of where the hurricanes will follow.